Well, welcome to an introduction to hypothesis testing. We're changing gears here, and you're going to be introduced to some of the inferential statistical tools in our toolbox during the last two modules of the term. I thought I would start today, though, with an Aggie joke. A Florida State student, a Kansas State student, and an Aggie all had committed horrendous crimes and were going to be shot. The FSU guys brought up, blindfolded, and the general shouted, "Ready, aim!" And the FSU guy shouted, "Hurricane!" Everybody ducked, and he ran away free. Dismayed at losing their prisoner, the guards brought up the KSU student with renewed vengeance. They blindfolded him, and the general commanded, "Ready, aim!" And the KSU guy shouted, "Tornado!" And fearing for their lives, everybody ducked, and he ran away free. Well, the Aggie has been watching all this and starts thinking. They all yelled natural disasters, and they got away, so I will too. So they brought him up, blindfolded him, and the general shouted, "Ready, aim!" And the Aggie screamed, "Fire!" I'm not really sure what happened to him. All right, I'm going to give you an example that will kind of introduce the notion of probability theory and probability to you. And it's a question that may have been asked in your town at some point in time. The question is, should one of the schools in town be renovated? And to answer this question, members of the school board sample 100 taxpayers and found that 70 said yes. So the question is, can we conclude that 70% of all taxpayers would favor such a renovation? And the answer is not necessarily. But before putting too much faith in it, we need to know as researchers how accurate the 70% is. We have to understand that chance plays a role when we sample. The error caused by chance factors must be taken into account when conclusions are drawn about the true state of affairs. The true state of affairs being what all taxpayers think about the school renovation. Chance is examined in terms of probability theory, and statistical inference is the application of probability theory. Now, don't be scared of probability. It's probably one of your least favorite math lessons that you had as a math student growing up. Probably the most frequently asked and answered probability question is, what is the probability of flipping a coin once and getting heads? And that would be 50%, because there's only two options. By definition, probability is how frequently a particular event of interest is likely to occur over a large number of trials. Probability is given as a proportion, and as such is given as a number between 0 and 1. Now, we've actually talked a little bit about probability thus far this term in terms of the normal curve. Because the normal curve is a theoretical probability distribution. By the way, you will be doing a little exercise with some M&Ms. I thought that would be a little more fun for you than flipping a coin, so that's why the M&M characters are on the screen. But let's look at probability and the normal curve. Again, the normal curve is a theoretical probability distribution. It specifies the relationship between area and units of standard deviation. So what you see on the screen is an example where we've measured height. The average height is 69 inches. Standard deviation of the heights is 3 inches. And so the question is, what is the probability of selecting someone who is between 66 and 72 inches? To answer that question, we have to change those raw scores to z-scores. And again, I made the math pretty easy. The z-score for 66 is -1. The z-score for 72 is +1. So those raw scores are at one standard deviation below the mean and one standard deviation above the mean. And we can hopefully recall from our study of the normal curve that 68% of the normal curve is within one standard deviation above and below the mean. So the answer to our question is the probability of selecting someone who is between 66 and 72 inches is 68 times out of 100. Now, one of the things I want you to start getting used to is the notion of not the things in the middle of the distribution so much, but those things that happen out in the tails. And so get used to thinking about observations that occur only 5% of the time, or 5 out of 100 times, or those items that happen 1 out of 100 or 1% of the time are considered very unlikely. We're going to consider them to have happened because of chance. Now you need to meet a new friend called the standard error of the mean, and I've got two new symbols up there for you. Mu is the symbol that stands for the population mean, and sigma is the symbol that stands for population standard deviation. So let's say somewhere out there there's a population of people, and on some variable interest the average score, if we had access to all the people in the population, would be 100, and the standard deviation of whatever it is that we're measuring would be 16. But it's also say that, like is true in real world, that we don't have access to the whole entire population, so we don't know that mu is 100 and we don't know that sigma is 16. So if we sampled 64 people out of that population, will the mean and standard deviation of that sample be 100 and 16 respectively? And the answer to that is probably not, due to sampling error. So even though theoretically the population mean is 100 and theoretically the population standard deviation is 16, any one sample that we might draw, the mean is probably not going to be exactly 100 and standard deviation probably not 16, and that's due to chance or to sampling error. So let's talk a little bit about this sampling distribution of means. This is probably some of the more theoretical stuff that we're going to be talking about, but a sampling distribution of means is created when you take a very large number of samples. So I picked a large number, 1,000, and you sample 1,000 times 64 people. So just imagine that we've got a big pot of everyone in the population, in that their name in our pot. We pull out 64 people, measure them on something, take the average of that, and set that average aside. We throw all 64 names back into our pot, mix them up again, select sample number 2, measure them, and calculate the mean for that second sample. So now we've got 2 means. We throw those 64 names back into a pot, mix them up, select our third sample, measure them on whatever it is we're measuring them on, calculate the mean for that, and now we have 3 means. Let's say that we do that 1,000 times, and so we have 1,000 means, and if we graph that into a frequency distribution, we have created a sampling distribution of means. So a sampling distribution of means is when you take a large number of samples, and in this case I picked 64, and that's kind of important. You'll see that in a minute. So when 1,000 samples are taken and the means of each of those samples are calculated and then graphed into a frequency distribution, that is called a sampling distribution of means. Now that becomes important in inferential statistics because of something called the central limit theorem. The central limit theorem says that the sampling distribution of means will be normal. And what's interesting is that it will be normal regardless of the shape of the raw score distribution. So take a glance over here to the right hand side, and let's say that whatever it is that we're measuring here is the distribution of raw scores for that item that we're measuring. And very quickly you can see that this distribution is very far from being normally distributed. But if we did take 1,000 samples, calculated the mean of each of those samples and put it into a frequency distribution, that sampling distribution of means would be normal regardless of the shape of the raw score distribution. The second thing that we know about the standard error of the mean is that the mean of that distribution will be equal to the population mean. And so here is our population again. Its mean is 16, And here are two sampling distributions of the mean, taken, these 1,000 samples taken from that population. And notice that the mean of each of these distributions is equal to the mean of the population. And so x, this x bar or m, so the sample, the mean of the sampling distribution of means, which I'm using capital M, will be equal to mu, which is the population mean. And then the last thing that you see here is that the standard deviation of the sampling distribution is something called the standard error of the mean. And so I've got the symbol here for that, SE sub m. There's various other ways that sometimes this is written. S sub x bar or SE sub x bar, but with me typing, that's the best way for me to represent it. Now, what we're going to find is that because we typically, again, don't know the population mean and standard deviation, we have to estimate that. And we're going to estimate the standard deviation of this sampling distribution of means, again, which is known as the standard error of the mean, by taking our one sample, because typically when we do research, we don't do 1,000 samples. We only do one sample. So we're going to take the standard deviation of our one sample and divide it by the square root of n. So n being the number of people in our sample. So let's take a look at a couple of things here, kind of using standard error of the mean and what we know about our sampling distribution of means. And I've got three examples here. The first one is a sample is drawn. The mean of that sample is 75. The standard deviation is 16, and it is size 64. If we calculate the standard error of the mean, what we find is 16 divided by the square root of 64, so 16 divided by 8 is 2. That is a measure of the margin of error that we need to keep in mind when we are interpreting 75. And so we can calculate something called the 68% confidence interval for the mean. Remember, 68% of the scores would be between the mean and one standard deviation above and one standard deviation below. And stop and think. Standard error of the mean is a form of a standard deviation. It is the standard deviation of the sampling distribution of means. So when we are talking about the mean of this one sample, we would be confident in saying that 68 times out of 100, the mean of the population would be between 73 and 77. Let's look at this second example. If the mean is 75, standard deviation is 16, and n is 128, this is just represents for you what happens with larger sample sizes. The standard error of the mean is equal to 16 divided by the square root of 128. So 16 divided by 11.3 gives you a standard error of the mean of 1.41. Likewise, we can calculate the 68% confidence interval for the mean, and notice that as our sample size goes up, what happens to our standard error of the mean? It goes down. And what that means is that we have greater confidence when we interpret what the mean of the population is. Because remember, this mean is just our sample mean. It's an estimation of the population mean. And then in the last example, we've got a mean of 75, standard deviation is 5, and n is equal to 128. If we calculate the standard error of the mean, it is 5 divided by the square root of 128. So 5 divided by 11.31 is 0.44. And notice again what happens. We have a much tighter, if you will, or smaller 68% confidence interval for the mean. Kind of the purpose of this demonstration is to show you that where we don't have much control over the standard deviation of our sample, quite often we do have control over our sample size. And so typically larger samples are going to be better because number one, we do have control over it, and two, it does result in everything else being even, it does result in a smaller standard error of the mean. All right, let's move on and talk a little bit more about inferential statistics. As a reminder, inferential statistics, our definition is making decisions with incomplete data, and we use that definition because when we conduct research, we typically do not have access to everyone in a population because populations typically are quite large, and because of time and money, we don't have access to everyone. And so what we do have to do is take a sample from the population, test whatever it is that we're testing, and then make inferences or generalizations back to the population. So again, a population is by definition a group of people that have at least one characteristic in common, and a sample is a subset of that population. And again, I'm just going to remind you that sampling error occurs anytime that we look at samples. We try to reduce our sampling error to as small amount as possible by using good research methods, but we're never ever going to be able to take out the chance variables. So there is no perfect research. All right, let's take a look at what is a hypothesis. It's a prediction about the relationship between two variables. When we talk about hypotheses from a research perspective, there are two types, the null hypothesis and the research hypothesis. Another name for research hypothesis is alternative hypothesis, and there are two types of alternative hypotheses. One's called non-directional, one is called directional. So let's look at the null. The null is a statement of equality between the variables. For our purposes, we're going to state in words the null in this form. There is no difference between whatever you have identified as your dependent variable and the levels of the independent variable. And I'll give you an example in a few minutes, and you'll see this written out in more specific terms. Now, two things are really important that you understand about the null. It is our starting point. It is what we accept to be true until we have evidence that gives us information that says that it's not true. So it is the state of affairs that is accepted as true in the absence of any other information. It is also the benchmark, and what we mean by that is that it is the hypothesis that is tested by the data. And if you think about it, what's the name of this set of PowerPoints? Introduction to Hypothesis Testing. And so the specific hypothesis that is tested is the null hypothesis. So here's a specific example of the null hypothesis. There is no difference in 100-yard dash time when trained using method A versus method B. So again, our dependent variable would be 100-yard dash time. Method A is some form of training. Method B is another form of training. So again, these are the levels of our independent variable. Again, given no other information, we have to believe that there is no difference between the groups. And we assume this to be true until our data demonstrate it. And I keep pointing that out because the data helps you test the null hypothesis. If there are differences, what could explain the differences? Some of the things that we would try to reduce their effect would be things like the wind. If I go out on two separate days, one day is windy, one day is not so windy, and have people run 100-yard dash times, that wind could affect their time. It could be that one of my groups starts doing some extra training. It could be that one of the groups is inherently stronger. So let's say that one of my groups is comprised of one of the Aggie sports teams. They're probably inherently stronger than the general student population. I may have faulty measurement equipment that's not calibrated. And then something that is always going to be an explanation or a potential explanation is chance. What I do want you to know is that everything but chance you should be able to alleviate as a possible explanation for the differences again, by using good research methods. We'll never take chance out of the equation. So let's look at our null hypothesis, or some more information about the null hypothesis and writing them. Again, as researchers, we try to eliminate chance as an explanation while attributing the differences to the type of training. Again, we're never going to be perfect in eliminating chance, but we want to reduce it to as small a degree or as small a possibility as possible. When we state null hypotheses, they are stated in terms of the population, which means that we use Greek symbols. So when we write null hypothesis, here's one form. Here is the symbol for the null, H sub O colon is, so the null is mu sub A. So this stands actually for the population of people who would be trained using method A, is equal to mu sub B. Again, mu sub B being the population of people who would be trained using method B. Another way that you could say that is that mu sub A minus mu sub B is equal to 0. All right, let's look at our research or alternative hypotheses. A research hypothesis in general is a definitive statement that there is a difference between the means. Think back to what the null said. The null said there is no difference between. These are statements of inequality, and because they represent statistics. Remember, population is to parameter as sample is to statistic, or statistic is to sample. Because we're using samples, then we have to use our Roman symbols. And again, we'll do that talk about that when we write them here in just a second. So let's talk about a non-directional research hypothesis. A non-directional research hypothesis says that there is a difference between the groups, but the direction of the difference is not specified. So for our data, our non-directional research hypothesis might be there is a difference in 100-yard dash times when trained using method A versus method B. So that's how we would write it in words. Here's how we would write it in symbols. The symbol for our research hypothesis or our alternative hypothesis is, so I would say this as H sub A colon X bar A. So the mean of the sample in group A is not equal to X bar B. And again, it's a non-directional test. We're just simply saying that there is a difference. It is a statement of inequality. So the mathematical symbol that we put here is not equal to. When we do use a non-directional research hypothesis, that does result in something called a two-tailed test. And we'll examine that a little bit later. But just start trying to remember and think about a non-directional research hypothesis results in a two-tailed test. Let's look at a directional hypothesis. Directional hypothesis reflects a difference between the groups, but in a specific direction. So here is an example of a directional alternative hypothesis in words. Method A will result in faster 100-yard dash times when compared to method B. So again, here are our Roman letters that we'll use to represent this. From a symbol perspective, H sub A is X bar A less than X bar B. And again, I use less than here because faster 100-yard dash times would be smaller. Okay, so that reflects that method A results in better times, if you will. And then also start remembering that a directional research hypothesis results in something called a one-tailed test. All right, let's look at the steps in hypothesis testing. The first thing you're always going to do is state the null hypothesis and the alternative hypothesis. You're going to do an exercise for homework after you've watched this where I ask you to write in words and symbols the null in both types of alternative hypotheses. In reality, you're always going to write the null, and you're only going to write one of the alternative hypotheses. So only one form of the alternative hypothesis when we actually start doing hypothesis testing. Step number 2 is establish the level of risk, also known as your level of significance, and also known as alpha. So level of risk for our purposes now says how many times out of 100 are we willing to make the wrong decision. Again, because we can never be 100% sure that we're making the correct decision. So there's always some level of risk, and the risk is that we make the wrong decision. Step number 3 is select the appropriate test statistic. In this class, we're going to be talking about only t-tests, and there's going to be 2 different types of tests. But if you continue your graduate career, there's all sorts of statistical tests that you might use here. And so selecting the appropriate test statistic is step 3. Step 4 is actually doing the math. So compute the test statistic, also called the observed or the obtained value. You've actually been introduced to this in, I believe it was at the end of Module 2 in your link to the future there. So the symbol for this was T sub O. So you've actually seen T sub O before. Step number 5 is determine the value needed to reject the null hypothesis. The term for that is critical value, and again, you've been exposed to this. That is T sub C. So determine the critical value needed to reject the null hypothesis. That critical value is something that we will look up in a table. We'll talk about that a little bit later. For now, just know that it depends on the type of test. So we're going to be looking up critical values for a t-test. It depends on the number of tails, so one-tail test versus a two-tail test. And think for yourself, what is tails related to? Hopefully you said that the form of the alternative hypothesis. So again, as a review, if you select to do a one-tail test, that means you have written a directional alternative hypothesis. If you do a two-tailed test, that means that you have selected to use a non-directional alternative hypothesis. And then the other factor that comes into play is our level of risk, or our alpha level. So think back even really to our that second or third link to the future in Module 2. You were exposed to some alphas there. Alpha is 0.01, alpha of a 0.05. The interpretation of that is for alpha of 0.01, one time in 100 we are willing to make the wrong decision or be wrong about our decision. Alpha 0.05 says that we're willing to be wrong or make the wrong decision 5 times out of 100. And so we'll be working with this a little bit later. Step number 6, 7, and 8. 6 is compare the obtained value to the critical value. That's exactly what you did in Link to the Future 3. You didn't know you were doing it then, but you're actually doing step number 6. More good news, you've actually also been exposed to making your decision. And your decision is going to be one of 2 forms, reject the null hypothesis or fail to reject the null hypothesis. And then step number 8 is to interpret your results. And I'll be working with you, or we'll be working with this when we start working on some of the math. Now, just a few other things we need to consider. The first one is, and I've thrown around the terminology, statistically significant or statistical significance. If we say that something is, or there was a statistical difference, let's say, between the 100-yard dash times using method A versus method B, what we are suggesting is that that was due to some systematic influence. In this example, that systematic influence would be the method of training. What we're also suggesting is that that difference that we observed was not due to chance. So again, statistical significance suggests that the difference, and I'll just use our example here, if we found that method A, or 100-yard dash times for method A, was statistically different from method B, what we are suggesting is that the difference is due to one of the training methods being better, not due to chance. Again, if we're working at the 0.05 level, that's our alpha level. What we're saying is that it could have happened by chance 5 times out of 100. Or if we're working at the 0.01 level, it could have happened 1 time out of 100 by chance. But 95 times out of 100 or 99 times out of 100, what we're suggesting is it was due to the fact that one of the training methods was actually better. So here's that example. So if our method A times were 12.3, our method B times were 15.5. Notice that those are different numbers. So there is a difference in runtime. But the question is not, is there a difference? The question is there a statistical difference? And if we found that there was a statistical difference, what we are saying is that that difference is not due to chance. It is due to the fact that, in this case, method A is a better method of training. All right, what if we're wrong? What if we don't account for those outside variables? And again, those outside variables we can take care of if we do use good research methods. Again, the only one that we can't entirely eliminate is chance. But what if we don't account for them and there really is no difference in the methods? We have to accept that. There is no perfect test. There is no perfect research, and there will always be some amount of error or some amount of chance that we cannot control. So think back to probably 4, 5, or 6 or 8 slides ago. Theoretically, out there on some measure within the population, there's a population average 100 with a standard deviation of 16. If we went out and selected 64 people or 100 people and measured them on that variable and calculated the mean, how likely is it that that mean of that one sample is going to match exactly the population mean and standard deviation? And it's probably not going to happen. Okay, the level of risk or the level of chance that we are willing to take, again, is expressed in our level of significance or significant level, also known as alpha. And again, the one that we're going to be most married to, if you will, is P is equal to 0.05. And again, what that suggests is that 5 times out of 100, the difference that we observed was not due to training, but due to some other reason, chance. All right, the last thing that we need to look at here is the types of errors that we might make when we are conducting research. And there are 2 types of errors that we might make. They are called a type 1 error and a type 2 error. All right, a type 1 error is the degree of risk you're willing to take that you will reject a null hypothesis when it is actually true. That is important because it is that type of error, that type 1 error, is specifically related to alpha. And who controls alpha? The researcher controls alpha. A type 2 error is failing to reject the null hypothesis when it is actually false. That is known as beta. It is related to power, the power of your test. I'm just going to introduce you to those terms right now. A little bit later on, before we finish the term here, I'm going to actually introduce you to a table that explains that. But I think what you need to do right now is just start learning to do some of the math, do some of the go through all of the steps of statistical testing, and then this concept will make much more sense to you a little bit later on.